Welcome everyone to this very special event, which takes place at the Department of Microtechnology and Nanoscience, MC2, at Chalmers University of Technology in Gothenburg, Sweden, where technology licentiate Ewa Simpanen will defend her PhD thesis with the title Longer Wavelength Gallium Arsenide-based VCSELs for Extended Reach Optical Interconnects. My name is Dag Winkler, and I am professor at this department in physics, and I will chair this session here. The work has been performed at MC2, at NFL, and with the epitaxial layers from IQE Europe in the UK, and financed by HP with a package, SSF and VR. Supervisor and examiner is Professor Anders Larsson. Can we have a We won't see him in the picture here, or no, okay. And co-supervised also by Associate Professor Johan Gustafsson. To scrutinize the work, we're very pleased to have our faculty opponent, Dr. Nikki Chitika from Piniser in Sweden. We also have a grading committee, which will then take the final decision of the outcome of this thesis, and that consists of Professor Kerstin Even from DTU, Professor Lena Bosinska from Chalmers, and Docent Richard Schatz from Royal Institute of Technology. And the procedure today will be the following. First, Dr. Nikki Chitika will give an introduction to the topic, the background to this work, and then followed by Ewa's presentation about her thesis work. Then the normal procedure is, of course, then that the opponent raises question to the respondent to see if the respondent has understood what she has done, and also to see if the science is good and sound. And then after that, the grading committee will have the chance to raise questions. And when the opponent and the grading committee are happy with the answers, then the thesis defense is open to the public for questions.
Okay, thank you. Thank you very much. So we have this mature technology based on gallium arsenide VCSEL arrays supporting interconnect infrastructure in data centers today and in supercomputers and so on. But so, what's the need to improve then? And what we have seen over the past few years is that the data centers are getting larger. So whereas in the earlier days, one would have a couple of racks in a room, or maybe several floors in a building. Now a data center will become the size of a football field, or even larger. And in the upper right corner, you have a picture from a data center that Google is building in Belgium, for instance. It's a huge size, and of course that requires in interconnects covering these distances in the range of from 1 to 2 kilometers. So if we look a little bit kind of qualitative picture, I try to show here the green bars at the lower side of the slide are showing a kind of reach that various types of interconnects cover in the data center. So we have the board-to-board or within a rack. It's up to 10 meters, and then between different racks, rack to rack, it's from 10 to maybe 100 meter maximum. And then from 100 meter, we will need to bridge to 1 kilometer and 2 kilometers, based on the evolution of the data center today. And of course, we have this technology based on VCSEL arrays and multimode fiber, essentially gallium arsenide emitting around 850 nanometer, which is very well suited for the short reach, the very short reach up to about 100 meter. Of course, it says here 100 to 300 meter, but that is, of course, dependent on the data rate per channel. When we are at 28 to 56 gigabit per second, that reach is rather limited to about 100 meter today. They support massively parallel links. Yeah, so many channels that do not need maxing or demaxing. That is important to reduce power consumption and as well to reduce latency. And one usually refers to this very short reach links as no latency or very, very short latency links. And then at the other extreme, we have the edge-emitting laser-based communication links with single-mode fibers, typically 1300 nanometer emitters. They can support some channel count, 4 to 16 channels per module. Today, maybe 1 to 2 fibers with 4 to 8 wavelengths per fiber, coarse WDM, and probably up to 112 gigabit per second per channel today. What is very good with the edge-emitting technology at 1300 is that can easily go 1 to 10 kilometers. And there is some latency, but it's moderate. This is primarily due to the maxing and demaxing and clock data recovery that needs to be done for especially going 2 kilometers and longer. But as we see on the blue line above, the edge emitters are good down to some kilometer, but then below 1 kilometer, the issue is that they do not scale well for the large channel count and low latency that we need on the shorter links. At the same time, the multimode fibers cannot reach beyond the 100 meter, especially at the higher data rates. And we would expect that even 100 meter would be difficult if we try to increase the data rate per channel beyond 56 gigabit per second. So we have some kind of gap between 100 meter and 1 kilometer. And in my opinion, one of or should I say the preferred solution should be to try to extend the reach of the VCSEL array-based technology, and that is because that will bring all the benefits of the massive parallelity that this technology and low cost and low power consumption per bit or per data rate, right? So here comes Ewa's contribution that she will present today. I think this is a very important topic today for pushing forward the communication capability in the data center, improving performance, making possible to increase the interconnection density also between 100 meter and 1 kilometer. I think this is critical for the continued development in the direction we have seen the last few years. Yes, thank you.
Thank you, Nicky. So then it's time for Ewa to present her thesis work. So welcome up to the stage.
Thank you. All right. Hello, everyone. So my work is titled Longer Wavelength Gallium Arsenide-based VCSELs for Extended Reach Optical Interconnects, where the VCSEL is a type of laser, and I will jump right into why the Extended Reach Optical Interconnect is needed. So most of you are familiar with large service providers such as Facebook and Google.
Sorry, Eva, could you share your screen so we see the viewers?
It's not shared, okay. Sorry, of course. Of course. It's here. I think. Screen 2. Share.
Yeah.
Isn't this good?
And yeah, now it's good. Thank you.
So, yes, sorry. And I will use pointer option laser. So, as I was saying, most of you are familiar with the Google and Facebook, which are very large service providers. And to you, it will come as no surprise to hear that most of the data center traffic to end user is with video streaming. However, businesses take up most of the traffic inside the data centers, and the cloud edge computing advances in co-location as well as hosting is increasing this demand. So the better part of the traffic of a data center takes place within the data center. Here, big data, I think we can see it if I point. I don't think you should do that. Thank you, Peter. Oh, sorry. Too much. Do we need the top of the slide, maybe? So, all right. So, yes, inside the data center, big data is the biggest increasing application. Data centers are exploding in size in order to accommodate for this traffic demand. And the major incentive for this is sustainability. That's why hyperscale data centers that are enormous in size differ from traditional DCs by they make use of the advanced infrastructure, and they use state-of-the-art power, cooling, telecommunications, artificial intelligence, operations, and software and hardware in order to make truly energy efficient data traffic. And by this year, hyperscale data centers will house less than half of all data center servers, but the hyperscale data centers will be processing, will be doing 68% of the processing, and it will store more than 57% or 57% of the data that is stored in the world. And if we then take a look at the energy demand by data center type, hyperscale data centers only take up 40% of the energy. So it's all about sharing resources under the same roof. This is the largest data center in the world. It's owned by Range International Information Group and it's situated in Langfang, China. It's almost 600,000 square meters large. Another company that caught my eye was Switch. They have marketed themselves as a as being a sustainable service provider, and they put effort into the entire infrastructure of the data center in order to provide energy efficient solutions. And they have a Citadel campus that has several data centers, but together they consist of more than 1.6 million square meters. And I encourage you all to take a look at their video gallery at switch.com. Especially, I wanted to show this movie, but due to the circumstances, I would like you to yourself go into this website and take a look at the core campus video. And they have a section in it that shows over 1 mile of server corridors, which is pretty cool. So it is easy to then understand why up to 2 kilometers of optical interconnects are needed. So this is the outline for the rest of the talk. So far, we have gone through why this healthy development towards hyperscale data centers raised the need for these energy efficient, high-speed, and long-reach optical interconnects. A long-reach optical interconnect could open up possibilities to use new and better ways of connecting servers in these data centers. And a typical architecture is shown in this image here. If you use a powerful architecture to connect the servers and components that go with it, you can substantially improve the energy efficiency, the capacity, and also the speed of data center traffic. So we will wonder then what is a good approach, and there are many options to choose from, and we will take a look at those options, but also motivate why we chose the gallium arsenide VCSEL, and then especially why we chose to focus on 1060 nanometer gallium arsenide VCSELs before we go into the choice of fiber and a little bit about the design. So that's what's coming up. So the vertical cavity surface emitting laser, the VCSEL, has a circular output beam, and compared to a edge emitting laser, for instance, this one, the vertical surface emitting laser, emits light vertically to the active region, which is indicated in red here. And the circular output beam fits great with the circular core of a fiber. And the detector in the other end of an optical interconnect detects the light. So the way the VCSEL is structured makes it good for 2D array fabrication. You can do on-wafer testing. If you've seen the front page of my thesis, you see an array of VCSELs. You can fabricate them next to each other, and it allows for flexibility in design as well. And the small active region of a VCSEL will also allow for a low threshold and driving current, as well as low power consumption. And direct modulation can be made very high speed. This is often packaged as an active optical cable, the VCSEL, the fiber, and the detector, along with some other components. And this is a standardized solution at the wavelength of 850 nanometers. Then you use a multi-mode VCSEL and a multi-mode fiber. These standardized multi-mode optical interconnects have a limited reach. They usually are limited to about 100 meters, at the speed of 25 gigabits per second. If you lower the speed, you can go further. But at that bit rate, it's about 100 meters, and it's mainly due to chromatic dispersion and attenuation in the fiber. So, other technologies that could be used, except for this top one, short wavelength 850 nanometer using multimode VCSEL, multimode fiber, are a longer wavelength, so 1310 and 1550 nanometer single mode VCSELs, edge emitting lasers, electro-absorption modulated lasers, and single mode fiber. You can also use silicon photonics, which is as well available in coherent technology as coherent technology. But the gallium arsenide VCSEL-based optical interconnects are, as we saw in the previous slide, superior. They provide a superior cost and power efficient solution because of the VCSEL is superior to the edge emitting laser, for instance, because of this. And then we have the VCSEL also has a small footprint. They can make a small footprint transceiver, and because of the gallium arsenide, we will encounter a lot of benefits as well, which I will discuss on the next slide. But how do we extend the reach? So these multimode optical interconnects were limited in reach. So how do we extend the reach with the gallium arsenide VCSEL-based technology? Well, our solution that we focused on was 1060 nanometer VCSELs. So with the gallium arsenide technology, we strained the quantum wells with indium in order to get to 1060 nanometers. And if we look at what happens in the fiber, we will have an improvement in the loss. So we will have half of the attenuation in the fiber, and we will have less than 2/3 of the chromatic dispersion when we move to the wavelength of 1060 compared to 850. And then when we look at the VCSEL improvements at this wavelength, the strain will move us from gallium arsenide with a bit of indium in the quantum wells. We will get to 1060, which means we will have strained InGaAs quantum wells, which will improve the speed of the VCSEL. And the quantum wells will be deeper, which can lower leakage currents, and the band gap will be smaller to lower drive voltages. You can also, since gallium arsenide becomes transparent at 1060, you can also use binary materials such as gallium arsenide, aluminium arsenide in the bottom of the device in order to get lower thermal impedance. Okay, so sorry for quickly jumping to the next slide, but this is about single mode and multimode VCSELs and single mode and multimode fiber. So just to explain the benefit here of using single mode VCSEL is that the standard optical interconnect using multimode VCSEL and multimode fiber has a VCSEL that emits in many modes. So except for this mode, the fundamental mode that usually has a very straight path through the fiber, you can also excite higher order modes in the fiber with the many modes of the VCSEL. This combination has a relaxed alignment tolerance, and but however, the reach of them was limited by modal and chromatic dispersion. And then if you instead use the same fiber, but you use a single mode VCSEL, with the help of selective modal launch, which is a special launch condition, you can reduce the effect of modal and chromatic dispersion in the fiber, which takes you further. But then if you use the single mode VCSEL together with a single mode fiber, which has a much smaller core, you will eliminate modal dispersion, and you will also reduce the effects of chromatic dispersion because you have only one fundamental mode propagating. So single mode VCSELs is of particular importance for longer reach optical interconnects, and that's why we, in my work, decided to focus a little bit more on single mode VCSELs. And how do we make a VCSEL single mode? Well, there are, here I present two ways to do it. So one way is to reduce the oxide aperture size, because the modes of a laser have a certain distribution, a spatial distribution. So by introducing, you can introduce loss or just narrow the oxide aperture, so the active region, the area that is used for lasing, you will cut off the higher order modes, and eventually, when the VCSEL is small enough, you will only have fundamental mode emission. And another way to get a more single mode design is to reduce current spreading to confine the optical gain. So we have two designs, design 1 and design 2, that we have developed and compared. And the difference between them is the distance between the oxide aperture, which confines carriers, is further from the active region in the first design than it is in the second design. It's a factor of 10 in distance between these designs. This makes, when you look at the spontaneous emission near fields, this makes current spreading around the active region, underneath the threshold. This was measured underneath the threshold. Current spreading is less in the more confined device, and that will give you an gain in a more confined area, which will give you more single mode emission, and also lower beam divergence. A benefit from a system point of view of single mode VCSELs is that they have small, single mode VCSELs have small spectral width, and also you don't have to worry about mode competition penalties. Okay, so also if we take a deeper dive into the VCSEL design and dynamics, we can see that a VCSEL behaves as it has a two-step. Oh God, the words escape me. We can describe the frequency behavior like this. So the dynamic behavior, if we increase at a certain frequency, the output of the VCSEL will the VCSEL will have a certain bandwidth, and we can see if the resonance frequency of the VCSEL is higher, the bandwidth will be larger, and the damping affects how much how peaked the response will be. And the active region plays a big part in this. We have our strained InGaAs quantum wells, which provide a higher differential gain. And that goes into the D factor here, which affects the resonance frequency. And the short cavity gives us a very strong optical confinement. We have DBRs, which are mirrors on each side of the active region, and they have been designed for a very low resistance and optical loss product. And a very important part in my work has been the top DBR reflection. So we can adjust the reflection on the very top of the VCSEL in order to optimize the photon lifetime of the device and therefore tune this damping. of the device and get a nice broadband or with high bandwidth response. So this comes into the equations over here. And then we have multiple oxide layers that reduces capacitance, and also very thick BCB around here to planarize the structure. And when we do that, we reduce pad capacitance. So both these reduce the parasitics of the device. And last but absolutely not least, the primary oxide layers. They are responsible to confine carriers, and we have a design. Our designs have very high internal quantum efficiency, and the oxides also are designed to be positioned in optical field nodes. So our designs are very weakly guided. All right, so now that we have taken a look at the VCSEL, the gallium arsenide VCSEL, we will quickly take a look at the challenges I've encountered in my work. So this is a little bit more fun. So I'm not going to go through all of the points here. I'm just going to highlight a few of the challenges I've had. And one is when you get the material, you have with including doping and graded interfaces, you have 400 layers that you need to validate and also perform oxidation tests. I do a lot of material simulations in order to perform etching in fabrication, and fabrication requires every feature of the VCSEL requires a pattern, and we design these patterns using CAD. And this is shipped during fabrication. So you see the many VCSELs on this chip, and the patterns are made by these masks. Fabrication, if you take a look at some of the points in fabrication, these are not all of them, but at some of these points you can see development that goes from putting out the mask, the pattern for the top contact, which is then deposited, and then following through, you have eventually finished device at the end here. And the lacing part is the very center part, the circle in the center. Another challenge is the setup design. The mechanical build can sometimes be complicated. Here we use a piezoelectric positioner in order to align a fiber to the output of the VCSEL that goes through a lens system. And components for testing isn't trivial at 1060. Not much is standardized. So, for instance, fibers has been in collaboration with Corning. They have provided us with fibers that are excellent at 1060 nanometers. Optimization is a big part. For instance, the VCSEL design needs to be optimized. Oxide apertures, mirror reflectivity, as I mentioned. Mesa sizes, we found that by reducing the size of the mesa, we could reduce the capacitance quite significantly. And when we choose driving conditions, so you need to choose an optimum point for driving the VCSEL in order to get the response you want, because it affects the dynamics and the large signal transmission with overshooting, ringing, and so on. And then noise reduction. I've made many measurements where I've measured noise, and measuring noise in a noisy environment is very challenging. And last but not least, again, revising theory and doing calculations and simulations. That's a big part of the work. So we are coming into the last part of the presentation, which is results and then straight to impact. So in papers A and B, we focused on single mode and multimode VCSELs. You see single mode emission here and multimode on the bottom. And then we can see that the bandwidth that I've mentioned is sufficient and nice for both of these designs, better for the smaller VCSEL in this case, which is the single mode one. So for both the single mode and multimode VCSEL, we made transmission experiments, and for the single mode VCSEL, we achieved, we tested 25, 40, and 50 gigabits per second at 2 different temperatures, and in back-to-back, which means without any long length of fiber, so very short length, almost 0 meters, we achieved 50 gigabits per second at 25 degrees Celsius. But with a fiber, a 1 kilometer fiber, we made preliminary measurements where we achieved 25 gigabits per second over 1 kilometer of multimode fiber using this single mode launch. And then in paper C and E, we measured frequency chirp, which happens when you modulate the VCSEL, and the VCSEL needs to undergo oscillations in order to stabilize at each voltage level. It will, in some turns, result in frequency chirp. And we saw that the chirp that happens, which is this peaking at the, if you look at the signal, zeros and ones, zeros, 1, 0, 0, 1s, you see that the frequency makes jumps. And we saw that this in combination with the negative fiber chromatic dispersion, it makes the pulse, the energy of the pulse will compress at a certain distance. So it compresses the pulse before it then again broadens. So there is an optimum distance for when we have a narrow pulse that can be transmitted this optimum distance. Let's see. So when we measured and gained our results for 40 gigabits per second over both 1 and 2 kilometers, we saw that when we went from back to back, which is the blue curve here at the higher rate, which was 40 gigabits, we saw a power penalty compared to when using the 1 kilometer long fiber. And then at 2 kilometers, we were back in the normal pattern where the pulse is broadening again. And then we also in paper E used pre-emphasis, is when you drive the VCSEL with a signal that isn't purely ones and zeros, but you have a pre-emphasis. And then we achieved 50 gigabits per second over 1 kilometer of SMF using this method. And then we also, in paper D, looked at noise performance. So we used single mode VCSELs again, but here we had tuned them. The top layer of the VCSEL, as I mentioned before, had been tuned for one with a very damped modulation bandwidth and one with a very resonant modulation response. And when we measured RIN for these two devices, we saw that the RIN with the damped, this is the damped VCSEL, was lower and actually came down to the noise floor very at higher bias currents, while for the peaking or resonant VCSEL, the relative intensity noise, the RIN, so its intensity noise of the VCSEL was much higher at these different frequencies. And we also measured the line width, so the relative intensity noise is a measure of intensity noise, while this amplitude noise, and this line width is a measure of the phase noise. So we measured the line width of the VCSEL, and we saw that the more resonant VCSEL had a much wider line width than the damped one. which is summarized here. So intensity and phase noise was strongly dependent on the resonator loss, but we actually saw almost no dependence on current confinement. It was very small. And the RIN went down to the shot noise level at higher currents for the damped VCSEL. And we also measured some of the smallest line width measured for single mode VCSELs. And in paper F, which is the last paper of my thesis, we investigated short reach OM5 transmission, starting with PAM4, which is pulse amplitude modulation. It basically means that we have 2 levels if we used PAM2. And this is represents a 0, and then you have a 1. So there we achieved 60 gigabits per second using equalization, which can be seen here. Both of these curves. One uses preemphasis. Both uses equalization, and one uses pulse shaping. And then PAM4, there's no difference in the spin-in felt movement, but when we use 4 levels, the equalized signal achieved 100 gigabits per second over 100 meters of OM5 fiber, and the equalized plus the pulse shaping gave us 110 gigabits per second, which is makes it suitable for WDM, which is wavelength division multiplexing. So this opens up for the possibility to use not only 1060, which is the wavelength I use, but also between the standard wavelength of 850 and 1060, you could use 30 nanometer intervals and have 8 carriers with data in the same fiber, which will lead to a very high aggregated speed. And the impact of my work. So first of all, I've made 1060 nanometer VCSELs that have shown state-of-the-art performance in terms of speed, noise, and efficiency. So that's one achievement. And then also I've provided lots of characterization, such as line width, chirp, and many more pieces of information about both VCSELs in general, and but in my case then about 1060 nanometer VCSELs. And then you can use these VCSELs in order to make single lane extended reach optical eyes. So one of these 1060 nanometer VCSELs together with fiber can provide a cost and energy efficient solution. And also in these architectures in the data centers, you could avoid a congestion limit by replacing many fibers that are shorter with one of these longer ones. And third, the aggregated terabit per second links with longer reach, which is one of the goals of the Ethernet standard. They are aiming to do 1.6 terabit Ethernet by adding parallel lines, so many optical interconnects next to each other, and then also employing this higher order modulation. PAM4 is most commonly used, and then also you can use the wavelength division multiplexing in order to reach aggregated speeds. And I would like, as a final slide, to acknowledge my collaborators, Hewlett-Packard Enterprise and Corning, Georgia-Tech, and Politecnico di Torino in Italy have all been contributing with their knowledge, and yes, it's been a good collaboration, while SSF and VR have funded the work, and IQE provided us with epitaxial material. I would like to thank you all for listening in, and the chair will take over and let us know what happens next. Thank you.
So thank you very much, Ewa. Great presentation.
I guess I could stand here.
at this moment, we would really like to have an opponent at the stage here, but can we get him up on the link, on the YouTube link or not? We cannot. So we will only hear the sound.
Yes.
So then I leave the word to the opponent, who will ask you some questions about the technical details and the science behind this.
Yes.
So please, make your round. Yeah. Good.
So thank you very much for a very interesting presentation, Eva. I think maybe you can sit as you did for the presentation. It's maybe going to take a little bit of time, our discussion.
Yes, I guess they don't need to see the top of the slide. In that case, I'll make it work.
Yes, right. So again, thank you very much. It was a very interesting presentation. Now we argue that VCSELs are very good, very well suited for optical interconnects, at least for the short reach. But why an optical interconnect? I mean, why do we need to go optical? What, you know, for the larger public, maybe this is a natural question to start with.
Yes, so in most homes and in older technology, you use electrical cables, and you still use electrical cables in the data centers as well, but it's a matter of application. And the reason for going to optical is because electrical cables, they depend on electrons to carry the signal. And that transmission generates heat. It's very, very, very lossy compared to optical transmission. Optical fibers rely on total internal reflection, and it could be considered lossless if it's ideal circumstances because of this. So mainly the loss, I would say, and the temperature generation in electrical cables. But then also there's so many benefits. You cannot tap an optical cable without this intercepting the signal. So it's much more secure in that sense. It's more lightweight. I'm not sure about cost, but silica is becoming much more easy to manufacture in large quantities. So yes, so complexity might be increased, but there are so many benefits with optical.
Right. So how long do you think one can go today at 25 gigabit per second electrical?
Well, we can go very long. It depends on what wavelength you choose. In data centers, we are limited by the latency. We don't want things to take too long, so we need to use a very high-speed technology. You said at 25 gigabits per second. I'm not sure the speeds they use in transatlantic cables, but in those systems they use wavelengths that have either the 1310 or the 1550. The 1310 is zero dispersion wavelength, and that 1550 is the very low attenuation.
Right. So optical, we know we can go 1,000 kilometers plus at the right wavelength with the right modulation format, right?
Yes.
So, but what about an electrical link at that speed? How do you think one can go electrical?
Oh, electrical. Okay, sorry. I guess it's would be an exponential decay of the signal. That's my guess, at least, that at 25 gigabits per second, I actually have no idea about the standards of electrical cables at that speed.
Yes, so what we have seen, just to put things in context for the optical interconnect, it's about a meter.
1 meter, wow. I would guess like 5 or 10, but 1 meter, yeah.
Right, so already at that point we understand that even at today's data rate, we can't get too far on an electrical cable. And then you touched a little bit earlier on these items. Of course, it's the weight, size. These cables that are for the electrical interconnect already at 10 gigabit per second, they were extremely heavy, taking a lot of space.
Yes.
And one of the key reasons going optical even before 25 gigabit per second was, for instance, the structural integrity of the data center building. They had to start go optical because of the weight the copper lanes will add to the concrete structure. It's kind of amazing and I would say unexpected in a way for us in the opto business. Anyway, so let's move to the next question. What do you think makes the VCSEL particularly interesting for this very short reach? If you would try to explain it to someone who is not directly in our field, it's
what makes the
why is the VCSEL such an appealing solution for the optical links?
Well, it is possible to make it very small. The circular, I mean, that's interesting, but for me, it's the small modal volume of VCSELs that make sure, because in optical interconnect short reach communication, we don't require very high power. You can distinguish between power levels that are much smaller than for some other applications. So you don't need a lot of output power or from the laser source or the light source. So VCSELs have the benefit of being able to have a very low threshold current, and you can operate them at very low currents in general. So the power efficiency is a big motivation between using VCSELs, and since the modal volume the structure makes them, you can manufacture them with a very small footprint, which is interesting for especially future generations of optical interconnect, because I believe that we will have much more integration and much more compact solutions that will actually require. Right now the VCSEL is in a huge, it's very small, but it's still a huge transceiver package, but I don't think that will be the case. So I think the footprint, the small footprints, is actually gonna be more important.
Right, and that of course in combination with its surface-emitting characteristics, so
Yes.
we can make arrays out of them.
Yes, you can do on-wafer testing. Cost is a huge driving factor in data centers and short-reach communication.
Good. So, what do you think would be some of the key characteristics that are important for an optical link? I'm thinking bandwidth, it's an obvious one, and we came several times to power consumption, but there are other things now.
Yes.
That will come to your mind first. You've been
the absolute first thing
yourself and trying to get to close the link in the lab, and you probably observe different key characteristics that you think are important for an optical link. Can you comment on this?
Yes, so you mentioned the bandwidth, so we want it to be high. But the second thing that comes to mind is linear conversion of the VCSELs. So you want the response to be as flat as possible. You don't want a lot of overshoot or very long oscillations that will give you, if the oscillations, the relaxation oscillations that occur as the VCSEL moves from one level to another are too long, you will have, it will interfere with the next bit if they don't well level out before the next bit starts. So that will give you timing jitter unless the dynamics of the VCSEL are optimum or optimized in some way. And then let's see, so we have the bandwidth and the linearity of the response. And then let's see. I had a few more, but they totally disappeared.
Well, take your time.
Let's see. Could you repeat the question once more so I just get in the same?
Yeah,
boat?
you know, I was thinking if besides bandwidth and power consumption, is there
yes, the power
any other thing, any other key parameter that you?
Oh yeah.
And of course, jitter and inter-symbol interference that is related to jitter.
Yes, I was thinking about the temperature stability of the VCSEL and the reliability. So from a system point of view, VCSELs break. So I want a reliable
optical modulation amplitude. How important do you think it is in the link? Or you were touching a little bit on this, saying that on a short link you don't need that much power. That's true. At some point, I guess the receiver needs some minimum amplitude to close the link.
Yes.
Please comment on
so
this.
yeah, you need to consider your power budget. It's especially for higher level modulation. You need to have enough power in order to be able to distinguish between 4 levels if you have PAM4. And usually you can see in the bit error rate, the sensitivity measurements that we make, that we have received optical power or potentially OMA on the x-axis. So the sensitivity of the detector, you need to have enough power in order for the detector to be able to pick up the signal, and in order to also distinguish between the levels when you decode. So that's, of course, is a big, and the fiber attenuates with 1 dB per kilometer at 1060. So that's 2 dB of loss if you go 2 kilometers.
Okay. So now you focused on single mode VCSELs, and yeah, why going single mode? Is that necessary, or is this something that we like to have? It's a nice to have, or is it a must, or where at what distance would become a necessity rather than good to have?
Well, so if you're looking at 1060, because we already know where the limitation is at 850, But if we look at 1060, I think it's a must-have still if you want to, because of the modal dispersion. If you want to, we haven't made a lot of tests with the multimode VCSEL and the multimode fiber, but I think it's still at a few hundred meters, less than half a kilometer, that you need to consider a single mode VCSEL. With the single mode VCSEL, we could, sorry for my bold language, but we could easily do 25 gigabit per second over 1 kilometer. It was a preliminary measurement and it worked just fine. Just switching from the multi-mode VCSEL to the single mode there was a huge step. And that's because of the mode competition and the modal dispersion. And now there are so many options coming up with fibers. They are looking into universal fiber, which is a few mode fiber, I guess, that has not, the multi-mode fiber has a 50 micron core, but this one has a 30 micron core. And I think they have a special alpha profile, like a refractive index profile of the core. But they claim that the nice to have with the multi-mode options is the relaxed alignment, which is cost efficient in transceivers. But they claim that with the universal fibers that don't have the very narrow core as the single mode, which is 9 or 7 micrometer core, they still can have that relaxed alignment tolerance with the universal fiber. And then they have, in those reports I've seen, they use a few mode fiber, not the single mode one at all times. There's been a few tests with single mode VCSELs as well, but they use few mode VCSELs and seem to get pretty good results. So I don't think it's as black as white as going from a multi-mode to a single mode. I think you can maybe have some options with a few mode VCSEL, perhaps with the right fiber up to 1 kilometer, I'm not sure. But then I think that single mode VCSELs are essential above 1 kilometer, absolutely. But I'm not so sure about the fiber option actually. Selective modal launch is powerful in order to achieve long distance over multi-mode fiber.
Right. So already at 850, there are some fibers today that we try to use the difference between propagation between different modes to compensate some of the chromatic, right?
Yeah.
Sure. So how have you worked with true single mode fiber at this wavelength, or is
not standard single mode, but we had Corning make us a optimized single mode. It was, the cutoff was changed to accommodate single mode transmission 1060. So the cutoff was around just under 1 micron. But Corning, the design was based on a standard model of a single mode fiber, only that they tweaked the cutoff frequency and reduced the cutoff frequency.
Okay. So how large is the core for such a fiber?
It was 9 micron, and then the mode field is a distribution, MFD, was 7.7, I think.
Yes. Okay, that's very exciting. We'll see now. Hopefully, development continues on the single mode VCSEL or around 1 micron wavelength, and that will, as you also mentioned, will drive the fiber development. So I hope there will be what should I say, an enhanced interest for the optimized fibers for 1 micron.
Yes.
Right. So let's dive a little bit into the VCSEL design and VCSEL technology itself. Now, we are discussing essentially gallium arsenide-based oxide confined VCSELs, but are there any other technologies that one may consider in this space?
Oh, yes.
Anything else but oxide confined or arsenide-based?
I'm glad you asked, actually. The first VCSELs at around 1060, above 1 micron, in this area that I'm working in, were made by NEC that used ion implantation in order to confine the carriers instead of oxides. Of course, you can choose not to do anything. You don't have to have an oxide. You don't have to use any more confinement than actually having the MESA, but then you would be susceptible to a lot of scattering loss and so on. So oxides reduce those problems significantly. Then you can choose to do ion implantation, which is it requires, if I'm not mistaken, a regrowth. So you etch a MESA to confine the carriers, and then I think you regrow with, or you implant. I'm not sure how that procedure is done, but it requires some fabrication that is complex in some way, as far as I understand it. I've never done ion implantation myself. And then you can also use a buried tunnel junction in order to get the lacing confined. And that it also requires some more complex fabrication, because you introduce you make a PN junction in the center of the device, and then you have to build a structure on top or around that. So it requires more complex fabrication. Oxidation is relatively simple to do, where you just expose your structure. We have aluminium in some of the layers, in a high aluminium content in some of the layers in our structure, and when exposed to water vapor at a certain temperature, they simply oxidize. And this introduces a little bit of strain, and it needs to be controlled, but it's relatively simple compared to the other methods.
Right. So what about the other material systems?
Yes, we have. You can make indium phosphide VCSELs. So with the indium phosphide, so the benefit of gallium arsenide is the manufacturability of the mirrors, mostly, because the mirrors can be made up out of lattice match materials, aluminium, gallium, and arsenide. If you look at the lattice constants of those, you can obtain a lattice matched DBR with reduced strain. And also, well, you can also do the same for indium phosphide if you have the right amount of indium. I guess you use InGaAs and then indium phosphide, and bury InGaAs and indium phosphide. So if you have a right amount of indium content in your InGaAs, then you can lattice match it with indium phosphide. But then the refractive index step between those material isn't as large. So that will require many more mirror pairs. So the mirrors will become large, or they will have many layers, which can be a downside. And you also have, let's see, you also have the free absorption, free carrier absorption is dependent on wavelength. So with the indium phosphide technology, you will have more problems with free carrier absorption, which is will give you more optical loss. It is the same with the difference between. So
you're trying actually with the gallium arsenide at 1 micron, you are trying to get the best out of both worlds. Right?
Yes, exactly.
So, what do you see as the key limitations of the gallium arsenide multi-mode VCSEL? Sure. We have in mind, of course, the single mode versus multi-mode difference. But is there anything else that you see is a key limitation that will force us to go looking into some other technology or some other type of design, except for the single mode versus multi-mode?
So you were asking about what is limited.
Yeah, I have in mind things like what's the intrinsic limitation
on the multimode
or noise or power consumption. So other things than the propagation itself, which of course might be.
And you're thinking multimode versus single mode.
No, I'm thinking more like this gallium arsenide traditional technology from the multi-mode VCSEL, the oxide confined essentially GaAs-based VCSELs, maybe with a little bit of indium in the.
Okay, Nikki. We were talking about single mode VCSELs and fabrication. And
yeah, the challenges you
yes. So
you've seen or you see trying to get the VCSELs operate single mode.
Yes. So in order to get the VCSELs operating single mode, a big part is the material design. So the epitaxial growth, all of these layers need to be designed properly. So that happens even before I start fabricating. And that per se is a challenge, because we would like to play around with moving the oxides, having them depending on how you design the neighboring layers around these the layers that oxidize. They can be have a very high oxidation rate or a slower one, which will give them a more tapered look. You can place them, you can design the optical field so that you can place them in nodes of the optical field, these oxide apertures, or you can place them slightly on the side of these field nodes, because if you place the oxides in a field node that's where the optical field is low, you will have less impact and less. You will have weaker guiding, which will give you a more single mode design. So we would like to play around with these things, test them, but since they are embedded in the material design, it's very hard to do iterations. What I can do during fabrication is I can, of course, find an optimum oxide aperture size, and I could play around with mode filters, which I have. For instance, we tried to or we have made successfully with the 850, we have etched a surface relief, a little ditch, for those of you who like that expression better, in the top of the VCSEL. So it's a circular hole, it's etched more in the center, in a circle in the center. And there, the reflectivity is optimum for the conditions you want to lace. But on the sides where we have less edge, you will have a worse, for those modes, a worse reflectivity, and thus it will not be prone to lace at the high probability. So you will, by doing that, you can force the VCSEL to become single mode, even though you have a larger oxide aperture. So that we've done a little bit, and also, I think most of the design to make it single mode happens before you actually fabricate it.
Right. But as you fabricate, you have variation in the process, for instance.
Yes.
And that will impact the ability of a particular design to deliver.
Yes.
What do you think was more critical based on your experience?
During entire fabrication?
Yes, during process.
I would actually say, like a minute ago, I said how easy it is to do oxidation. But oxidation isn't completely easy. You want to be able to control what kind of compounds you are making, and like the oxide, what gases or what materials you actually have in your oxide. When you oxidize, they will change in size. The material will introduce strain to the device. The temperature is critical. You should not go too high. You cannot go too low. It needs to be stable. So oxidation, and you can also, when you oxidize, you don't only subject the very high aluminium content layers to the water vapor. Your entire chip is subjected to this process, and you can get, if the edge on the other parts of the chip isn't protective enough of the surfaces, you can get cracks in your entire chip, and various things can happen.
Right. So now you mentioned the oxidation. Of course, is one of the key process steps there. And if I understood correctly, you were around 4 micron diameter with oxide aperture?
Yes, for our single mode design.
Right. So how critical is that dimension? What if one is 10% wrong from 4 micron? Are you falling off a cliff?
10%, no
just
problem.
Say 10% worse than the optic.
10% is no problem. There's not a lot of change in the statics or dynamics if you change the oxide aperture by 10%. What I see is, so say that this material D2, it becomes single mode at 4 microns. A 3.5 micron device will still perform. It will be hard to distinguish them. It will have a slightly higher resistance. But underneath, say 3 microns, when they become 2.5, we can't really make them 2, 2.5, 2.8, and 3, then you start to see that the resistance goes up significantly, like exponentially, almost. And I've also seen when I try these very, very small ones in large transmission, they are not as reliable as others. So the VCSELs I publish, they have been undergoing extensive measurements and have been tested for hours and hours and hours and hours. We've done some reliability measurements, but none that have targeted reliability. However, when the oxide aperture size was as small as 2.5, they tended to actually degrade quite quickly. So I think at some point, when you oxidize too far, you will have reliability issues, probably due to the strain and other defects. I've also seen that the oxides of those VCSELs, it could be basically dependent on the amount of time they have been oxidized. Maybe if the MESA was smaller and you made the oxide aperture 2.5 microns, it would be fine because the time to oxidize would be shorter. But when you had oxidized for a very long time, the oxides would be uneven. You could have defects very close to the center of the device, and that would cause problems with reliability.
All right, right. So you mentioned resistance going up very rapidly as the aperture gets slightly smaller. So is this as expected? I would say, scaling just with the area of the aperture, or do you see that the resistance?
So the resistance should be proportional to the mode. I think the mode volume somehow. I don't have the I'm a bit tense also, so I don't have the equations in my head. But when you reduce the oxide aperture size, it's not only, it's the area. You reduce a circular area. So yes. The resistance.
So when you, I'm sure you got VCSELs with a slightly wrong aperture compared to what you were targeting. Was your feeling that they kind of scales with the area of the aperture, or,
yes.
or did it be a more rapid change than?
At a certain point, it's more rapid, but I think that depends on other issues, such as almost closing the active region. So until they are 2.5 microns, it scales with the we made calculations on that, and it scales with the area, injection area.
Right. So that's as expected, so to say.
Yes.
Right. Thanks. So now let's look at multi-mode versus single mode and some other parameters. How, for instance, relative intensity noise, GR, bandwidth of the VCSEL. Can you try to give some kind of general trends for these parameters from what you have seen, and if that was as expected, or if you have seen something surprising in your experimental results? If we take, for instance, how ring changes with adjusting the size of the aperture, and other changes you need to make to get a VCSEL single mode. Which one gets a lower ring in the end at the operating point, and was that behavior as you were expecting, or were you surprised by it?
So ring, something that I can't say I was surprised, maybe, but RIN can be affected by optical feedback. But if you measure RIN on a single mode VCSEL, like in order to measure it, you need to couple the output to something, and that something might easily generate the feedback. So if you have any reflection or anything, you will get the VCSEL output back into your VCSEL. And single mode devices can be very sensitive to this. So, and that can definitely be seen in the RIN. And some of the RIN curves I measured, they look like pieces of art. Like someone took a like a paintbrush, and just threw the paint all over the place, because the VCSEL was being disturbed by optical feedback. So that's not even something, you can't see a pattern in that data.
Right.
So you have to make sure you don't have optical feedback into your laser if it's a single mode laser. Multi-mode VCSELs are a bit, because of the mode competition. In that case, the modes contribute to each other, and they are not as sensitive to optical feedback as this a single mode VCSEL is. Let's see, I was a little bit surprised at how low bias currents I found the RIN, because when you look at the measurements in hindsight, it's very easy to see the characteristic. We saw the peaking of the RIN at the resonance frequency, and you can see it goes from a very, in the single mode VCSELs, from a very low low frequency RIN up to the resonance peak where we have the most RIN, and then it goes back down again. So that pattern is very clear. But when I started measuring, I was measuring closer to 1 milliamp at devices of the same size as the ones I presented, and I did not see anything, because I had much, like when you develop a stage, you have much more noise in the beginning than after you've established your measurement method. So I could not see this behavior, and I was surprised that the peaking occurred at and that the RIN settled to the noise floor as quickly as it did. That was a surprise to me, but it wasn't a shocking amount, but it was still, so I had trouble finding the actual characteristics of the RIN in the noise in the noise.
Right. So, but now if you would compare your multi-mode device and the single mode one,
yeah,
and based on the experience you have now, is it a dramatic difference in RIN at the optimum operating point for transmission? You know, so what I have in mind is you need to reach
yes,
where you want to operate on large signal modulation.
So yeah.
Is it a major difference between a single mode and a multi-mode device? If I look at RIN, bandwidth, OMA, I can adjust optical modulation amplitude,
yes.
jitter, or are they kind of comparable? Of course, in the end they will reach a different distance and have different properties in a way. But at this more basic level, are they fundamentally different, or essentially they are more or less comparable?
So yes, that's a good question. So at 1060, we haven't published any of those results. At 850, we have a publication that shows that the difference between, as we move to a bias current where the RIN has settled, the multi-mode VCSEL will have a 10 to 15 dB higher RIN level. And what I saw with the 1060, when I've measured a few of my multi-mode VCSELs, I saw about the same behavior. So that was not a surprise, and it's about the same as for 850. The multimode VCSELs, because yes, of the many modes, they don't really settle at shot noise level. They settle at a higher level, about 10 to 15 dBs higher compared to single mode VCSELs.
Right, so that's a big difference.
Yes.
So how about bandwidth and optical modulation amplitude you reach with a single mode compared to the multi-mode device?
Yes, so...
now I mean bandwidth of the VCSEL itself, so you measure back to back.
So that's a tricky question for me, I think, because the multi-mode VCSELs we have are much larger in size than the single mode VCSELs we have.
Sure, but that's right. Yeah, they are multi-mode, they are bigger. Yeah. They are different devices, so to say.
Yes, but we do also have two devices that are differently strong single mode, like higher order mode suppression, and the ones that were less single mode, so more of multi-mode devices at the smaller aperture size. They become single mode at a much smaller aperture size than the second device. Those tended to have, let's see, I need to dig in my memory, slightly higher modulation, like a multimode, a larger VCSEL has a smaller modulation bandwidth. But when we measured and compared these two devices, there was a slight benefit to in modulation bandwidth for the one that was less prone to single mode behavior. But I can't really say that's a fact because I have to revisit those numbers. But it was a difference if the one design had a modulation bandwidth of 21 gigahertz, the design one had a 23, so it's a 2 gigahertz difference. But between the multimode, if we also include the size, multimode single mode, a larger VCSEL will have the smaller, in general, the smaller modulation bandwidth.
Yeah, okay, good. So how about jitter? Do you have any general comment, single mode versus multi-mode on VCSEL? Timing errors, so to say.
Well, a single mode VCSEL should have stronger gain suppression. So it should have a more damped response. And therefore, the overshoot and ringing should be less with the single mode device than a multi-mode device. And if I look at my experimental data, for instance, in the papers A and B, I said that we measured static and small signal on both single mode and multi-mode, but then I only showed a single mode long transmission results. It's because the multi-mode VCSEL performed slightly worse. It did achieve 40 gigabits per second back to back, but it did not come up to the 50 gigabit per second as the single mode VCSEL did. And the eyes, even at the same speeds, they look, it looks like jitter is a bigger problem with the multi-mode device.
Right. And you understand this based on the fundamental properties. Right?
Yes.
So it's not really a surprise.
No.
Okay, so what do you think one should focus for the future development now you brought this, you studied this topic and achieved very good results. What do you think someone should do to push this further? What should one focus on? What are the key elements we should look into?
I would, let's see. So I would love to see more epistructures, similar but with slight variations. It's not maybe a key thing to focus on, but it's something that will happen if more people focus on this type of device. I think the 1060, or it doesn't have to be 1060, it could be 1030, it could be 1050. But I think that range of VCSELs has a good use in future data centers. So I do believe people should focus on those, and then we will see more EPIs in this on this wavelength. So that will be interesting to see. But focusing then maybe on trying to achieve single mode, because I do think we're moving towards more single mode optical interconnect. So it could be with multimode fiber, universal fiber, or single mode fiber, but at least a single mode VCSEL. So I think one should focus on trying to integrate that into the design, as well as trying to come up with new ways to filter out the fundamental mode, or promote fundamental emission, fundamental mode emission. Because if, for instance, if you use a mode filter on top of, I personally, with my materials that I have now, I would love to make a larger oxide aperture, maybe a 6 micron size, so larger than the 4 micron that was single mode by the oxide aperture. So I would like to have that. It would have like resistance less than 100 ohms, maybe 80 ohms or so, which is beneficial. And then I would want to make a mode filter on top of it in order to make it single mode. That would give us a single mode VCSEL with low resistance and higher power, and that higher power could be used for PAM4, for instance. And I think that would be a very powerful device.
Right. So is now discussing the mode filtering. So is there any idea to say select the next order mode instead of the fundamental? Still single mode, but not the fundamental in the VCSEL.
That's the research that I think is pretty exciting. The more creative paths. I think we need to do more research in looking at what's the benefit of the other modes, because they do have a different spatial distribution. Maybe you can benefit from this in some way. Maybe you can use it with a special kind of fiber. I don't know enough about it, but I think that we should learn more about it. So.
Sure. Okay, good. So now, if we look at the transmission experiments you made, you tried 2 levels, so non-return to 0 essentially, and then
yes,
tried to account for the 4 level. Did you consider any other format, at least theoretically, or maybe even tried in the lab?
Yes.
And do you have a general comment related on which modulation format you believe to be more suitable. And now I would split this in two different cases. Say you only want to go 50 meter in one case, and say you want to go 1 kilometer in the other case.
Yes. I think for 50 meters, I would definitely consider PAM4, the 4-level modulation format, just because you increase the symbol rate by such a degree from just going from 2 levels to 4. And for 50 meters, we've already proven that we can do good, we have good results from 100 meters already with PAM4. Like there are other modulation formats as well, as you can add complexity there in various forms. But I do think the simplicity of the PAM4 is what is going to be used in standards today and also for the next 10 years maybe. Commercialized products are of course slower than the research, so maybe we'll see research into other modulation formats, but I still think PAM4 will due to the simplicity compared to increased more advanced modulation formats, PAM4 has its benefits. And with only 50 meters, the power will be enough for 4 levels, so I don't think you need to restrict yourself to 2 levels. You can make sure to have a well-suited response of the VCSEL in order to accommodate for the 4 levels. So yeah, PAM4 definitely. And then for 1 kilometer, not so sure there. Maybe we have your first question. If we tried something else, we tried duo binary modulation, which has, with some tweaks, it has 3 levels, 2 eye openings, and we saw some good results from that, but it's not very common in standards, at least. But that's a potential modulation format for the 1 kilometer case, where you might not be able to squeeze in 4 levels. But with 1060, if we could make that device I was just describing, it would be interesting to see if we can do PAM4 at 1 kilometer and 2. But without that device, I would say Juno binary or PAM2 so far at 1 or 2 kilometers, due to the need of. It's not that many dBs though. But so the chromatic dispersion also you still have some chromatic dispersion. You can't you can reduce the effects of chromatic dispersion by using a totally single mode system, but you will always have the chromatic dispersion effects there with the fiber. So due to that, I think you would need binary or dual binary.
Right. So yes, now it's true that the electrical domain has kind of set the standard at the moment. In any case, they settled for the 4 level, and unless you use some more complex electronics in the module, the preference would be to just transfer that to the optical domain. But I believe that maybe dual binary has more potential than, as you say, dispersions is limiting the bandwidth. But you measured chip. And I think that that was a very interesting measurement, and a little bit unusual at this wavelength.
Yes.
What's your view on this? What is going to be the impact of chirp in a link of, say, about 1 to 2 kilometers based on VCSELs? Is this going maybe to be some kind of fundamental limitation at some point, or you think there are ways to deal with chirp, maybe in the VCSEL design or somewhere else in the link?
Oh, well, yes. So what we saw when we investigated the chirp was that we got eye skews because the combination of the sign of the negative chromatic dispersion and the sign of the chirp, like the direction of the chirp, those in combination at like on the rise. During the rise time at that transient, because of that combination, you would experience, and the chirp was different at the beginning and the end of the transition. So you would experience that the rise time would be longer after transmission, and the fall time was shorter. So you got an eye skewing because of the chirp and the dispersion. So it can be a limiting factor, and let's see, how can you mitigate or take advantage of that? Maybe.
Is there anything we could do with the design of the VCSEL to at least reduce the impact of this effect?
Well, it all has to do with the dynamics and the the chirp, the frequency fluctuations in the VCSEL has to do with the small refractive index changes that happen as the signal settles to a level, to a power level. So it all has to do with the dynamics and the coupling between photons and electrons. So I would assume there is a way to mitigate the chirp, but I am at the time not aware of how to do that actually. So, but because it's all coupled to the fundamental behavior of the VCSEL, it should be possible to design to lower the effects of chirp.
Yes, so maybe this is a very interesting topic for someone else to.
Yeah. Yes, and since we saw the big effect on the skewing, I mean, maybe the skewing could benefit transmission and you could get a clearer eye, or yeah, it could be interesting.
Good. Thank you very much.
Thank you.
So, Nikki, you are happy with what you heard so far?
Yes, thank you very much. It was very good, very interesting discussion.
Yes, I'm also very happy about the discussion. It was very nice to hear your questions.
Do we have the committee online? Have you been able to follow the discussion?
Yes.
We have Professor Kristen Even from Technical University of Denmark. Would you like to start?
I can do that. Yeah. Can you hear me?
Yes.
All right, good. So, yeah, to start out with, I'd like to congratulate you on your work on producing some of the best high-speed VCSELs in the world. Continuing that work from your group. I also appreciate very much the careful and detailed measurements and analysis that you have presented, and I think it's a well-written thesis. I do have some scientific criticism, which is related to missing details to reproduce the work. So, I mean, if I were to copy your work, I would miss some details. Most importantly, details of the epitaxy and the process details.
Yes.
So this is probably on purpose, but I still want to mention that. Anyway, so some detailed questions. So you have these two designs where one of them has moved the oxide aperture to 17 nanometers to the active region, is what you write.
Yes.
So when I first saw that, I was thinking it was the distance to the quantum well, and that got me a bit worried about reliability. Why would that be?
Let's see. It would be. Ooh. Well, I'm thinking. I mean, the cavity needs to have a certain length, but I'm guessing you're thinking about something else than the actual cavity.
Yeah, something process related. So in reality, you don't have 17 nanometers to the quantum well. It's much bigger, as far as I can see.
The quantum wells are in the very center of the active region, and around the active region, we have a region of gallium arsenide, I think, on both sides.
Gallium arsenide phosphide, I guess.
Yes, and then on top of that, we have the mirror. So there's a buffer region, or to make this half lambda cavity.
And why is that important?
It makes that's in order to get the standing wave of the optical field, we want it to be half wavelength long.
Right. That's definitely one thing. But why it's important for reliability? In the old days, I guess, there have been a lot of debate about oxide-confined VCSELs and reliability and so on. What is that debate about?
Well, I guess the oxides introduce strain in probably one direction, while the quantum ones introduce strain in the other. So maybe you would get a skewing that would decrease the reliability.
Strain can do that, but you're doing these tapered apertures, which helps a lot there.
Yes, they are very thin and at the very tip of the taper.
But what is actually going on when you do this oxidation? I mean, the physics of that, the chemistry of that.
Well, not very. Let's see. So you do introduce water vapor and they oxidize the aluminium. It's all gas layers, and I think the oxides expand while you do the oxidation. But chemically, what kind of the oxides introduce a capacitance, but I'm not sure what you're grasping at.
Well, I'm basically asking you because you've done a lot of process development work.
Yes.
I guess in terms of time, that has been a huge amount of what you've been doing. So I'm just trying to dig a little bit into how much you actually went into the theory of those processes.
Yeah, the oxidation isn't my high point.
All right. Anyway, there will be some arsenic generated that will diffuse into the nearby areas, and if they go into the quantum well, that would be a problem. But you actually have a barrier, which when you have the first part of your thesis, the introduction part, so you can actually see that, but it's not clear from the papers themselves.
Nice, thank you.
Anyway, one thing that I was thinking about for these single mode VCSELs, I mean, what about the yield? I mean, Nikolai was a little bit into this also, but I mean, when you go from multi-mode to single mode, does that from a production perspective give you some issues?
Not with the, no, the yield is not different. It's in the cases where I oxidize way too far, like way more than 10% too much, then I see a yield difference. But as long as I'm targeting the between 3.5, 4 microns, and then the yield is the same as for the multimode devices.
Okay, so in practice it's not an issue.
No.
What about? I mean, you have this interesting technique where you adjust the top reflectivity.
Yes.
And so this was not discussed. Is that how is that done in practice? Is that a one iteration or is it many iterations? How do you do this?
It depends. It could be both. Ideally, if you do it in a large-scale fabrication, it's one step. In research, we could do it if we know how far we're gonna etch. We have 1D simulations that give us a relation between the slope efficiency, like when we measure the LIV curve, so the statics of the laser. We get a slope efficiency. I'm just explaining for anyone who doesn't follow. And that slope efficiency can be related to the photon lifetime. And we simulate that in 1D simulations. And so by measuring the slope efficiency, so you fabricate the device, measure the LIV, and then go back down and etch the amount you want to etch according to the simulations. But in the first time we do this, and we haven't tested this material before, we etch first once, maybe different amounts on neighboring VCSELs, or once on the same VCSEL, then again, and then again, and then again, to get several points and to really see where the photon lifetime is at its max and where it's at its lowest point, and the reflectivity as well. They are related.
But the theory actually fits with the experiment.
Yes, the only vague number there is the internal quantum efficiency. That's estimated from curve fitting.
Right, okay.
So that's the most risky parameter. But the trend is the same. So the trend, the max and mins will still occur at the same edge depths. But the internal quantum efficiency will lower or decrease the curves, both the photon lifetime and
yes,
slope efficiency.
Yeah, they are in one of your pages.
Yes.
Curves. All right, good. Then I also wanted you had something in your slides about you write that since it's a new epitaxy, you needed to do a lot of developments, and you had something on your slides. But maybe you could say, I mean, what were the main things you needed to develop going from the 850 to the 1060?
The main thing I had to develop. Let's see. We can. So you on YouTube can't really see all of the slide, but so I write here that we did material simulations, representation, and mask design. So when going from 850 to 1060, I needed to make sure, because the DBRs will be adjusted for 1060, and a DBR is based on the wavelength. So the mesa is taller in a 1060 device than it is in an 850. And also the compositions are a bit different. So I needed to validate the etch rates. I made this simulation that is shown on screen here, at least, is from transfer matrix method, an intensity. So I simulated the reflectivity through, if you look at the material from the top, so you have the entire epitaxial structure and the substrate in the bottom, you will get, if you emit with the laser on top of that, you will get a reflection. And I simulated that using the TMM. So when etching, we can actually in situ follow this these curves in order to know how deep we've etched into the epitaxial structure. So those simulations needed to be made. I also needed to develop the mask because the photolithography is very sensitive to, even if it's almost the same material as the 850, the photolithography will not come out the same. So all of those recipe times and developing times need to be adjusted in order to get good patterns in order to then deposit the and etch with a good precision. Let's see. I could actually remove one fabrication step from the process, which was in 850. We don't have as much binary materials in the bottom mirror, if any. So there we use a contact layer in the bottom. We etch first the top mesa to confine the active region and then oxidize. And then we etched a very tall bottom mesa and put the contacts in a contact layer underneath the bottom DBR. But in the 1060, we used intra-cavity contacts, and so that actually simplified fabrication a little bit. Yes, I changed the thickness of the metals in order to use them as I used the top contacts in my case as a mask because we wanted to reduce the mesa size to a much smaller one than we used before. It was 15 microns instead of 20. So I used the metal ring, the top contact, as a hard mask when etching. So I ran some tests and tested that, and then also.
Is that also the reason why you have smaller parasitics in paper C than paper B?
Yes, yes, it is. I think will take those as a highlight, and there's fabrication is including every lithography step. It's about 30 or so different sets. So there's a long way to go.
Yes. All right. I'll leave something for Richards and others also. But just one final question, which is probably difficult. So in paper C, you show a ring curve that goes. So in figure 6.
The alignment.
You have a ring curve that goes below the shot noise.
The ring.
You have a ring including shot noise that goes below the shot noise. So that is for the final question. Is that theoretically possible?
I'm guessing you mean this figure.
Yes.
Yes.
Yeah, so here you have ring including shot noise that goes below the shot noise.
No, it's not possible to see. Let's see. Yes, so it goes below the shot noise level, and it depends. Let's see if I can see it again. I shouldn't have put it down. Yes, around the frequencies of 5 gigahertz there.
And in some ranges.
Yeah, I'm gonna think so. The shot noise level is 4 milliamps. I mean, there is an uncertainty in the measurement, so but I do try to think if there was something that I've missed.
So this is probably an academic question, I would say. Practicalities is probably not so interesting, but what does the shot noise limit actually mean?
Well, the shot noise, it's a, so you have the thermal noise limit and the shot noise limit that usually limit your system, and then the shot noise is much lower than the thermal noise limit, and it depends on, it's related to the random events during photon generations, I think.
Yes.
So it's both in the VCSEL, and then also on the detector side, you will have this shot noise in the dark current of the photo detector. So there's shot noise coming in from at least 2 sources here, and you can't really measure, like that noise limit should set a noise floor for what you can measure. So you shouldn't be able to measure a signal below the noise floor, shot noise floor. But I believe that these curves are subject to maybe an error margin that when they reach the shot noise or something similar.
That may very well be true, but it is in fact possible to go below the shot noise.
Really?
If your generation of photons is not random. So this is something that was shown in the 80s that you can do if the current that you send to your laser has very little noise, then the photons you get out of it will also have less noise than the shot noise. Oh. Normally when you transmit, then it becomes phosphon in the end, but in this case you actually have a very efficient laser coupled with very low loss to your detector. So in theory, it could actually be true. It might also be an emission there.
Interesting. Thank you.
Thought it was interesting. That's probably more on the academic side. All right, but I think I'll pass on the word to the next one.
Thank you very much, Kristen.
Thank you.
So thank you. I think we go in distance, and closer to us, I guess, is Royal Institute of Technology. Well, it may not be.
I think actually we are the closest.
Yeah, you're the closest. But
yeah,
national-wise, let's go to the Royal Institute of Technology with Richard Schatz. Are you there? Hello? Richard?
Yes, I'm here.
Do you want to pose some questions to Eva?
Yes. First of all, thank you very much for inviting me here to the evaluation committee. And I want to say to Eva, it was a very nice thesis to read. It was nicely disposed and well written, I think.
Thank you.
And also it covers the entire range. I mean, from fabrication, characterization, analysis to system experiments. So it was a pleasure to read it.
Thank you.
Yeah, and I also want to say that I'm impressed by the clean modulation response and RIN measurements you have done, at Chalmers. So it's really nice to see that you can measure RIN in these devices with such a good dynamic range.
Yes.
I have 2 topics really to questions on. It will be a little bit more theoretical.
Ooh.
But it's first it's on sharp dispersion, and the second one will be on relative intensity noise.
Yes.
Yes. So when it comes to sharp dispersion, if we look at page 20, equation 3.9.
Yes.
Yes. There you have in the first parenthesis, you have the product of C times beta 2.
Yes.
So what is the sign of C and what is the sign of beta 2 in this expression?
Oh, well, for my devices or my fibers, beta 2, well, I would say, let's see, I just had a course on this, so I should know it. Well, I guess they together should have a negative sign, if I'm not mistaken.
Yes.
So
you measured this compression, or you saw this compression.
Yes, I have it in I would say that the beta 2 is negative and the chirp is positive.
Oh, I'm sorry.
It's the other way
it's
around.
Opposite.
I'm mixing it up.
Yes, the D is negative. You're correct. The D dispersion, but beta 2 is in fact positive. And C here is negative.
Yes, beta 2 depends on the dispersion. The dispersion is negative because it's the picosecond per nanometer kilometer. So that's the minus 31 of the fiber. And
yes,
then
but beta 2
is related to D by the equation in 310. Yes. So it becomes positive. And the chirp was measured. Where do I have it? Here. And yeah, the chirp, although this C is the theoretical C here is for a Gaussian pulse. So in order, this is a single mode VCSEL, so it's fairly Gaussian, but in order, you can't really derive it from the frequency chirp measurement that I have in this. You have to extract it in a different way. I just want to get it up on screen. This is the chirp measurements that I made. But yes, we did estimate the chirp, and I think we have a number in my paper here somewhere. I think we estimated it to somewhere around there, 2.1.
Yes, and it's a sound. So, but it will be negative 2.1.
Yeah, negative 2.1.
So how is this chirp parameter C related to the alpha parameter of a laser?
Oh, that's a good question. So in my work, we did in paper D, together with Pierluigi De Bernardi in Italy, we made a very long. Or do you mean the alpha parameter of the fiber?
No, of a laser.
Of the laser, yeah, good. Because Pierluigi made simulations of the alpha parameter, and I'm not really, like, he was part of that work mostly, and he has a very extensive model about how to extract the alpha parameter from the gain simulations. And how is it related to chirp? Well, let's see. Alpha is related to the carrier density. And the chirp has to do with the carrier and photon density, the rate equations at least, the coupling between them. So I'm not sure what the relation would be, but I can definitely see that there should be a relation between them.
Yes, I mean, in fact, in theory, if everything is perfect, C is just minus alpha.
Really?
Yeah.
C is minus alpha.
So if you
that's too easy.
You probably have an alpha parameter around 2.2 in your laser or in your laser material, but that would be interesting to see. I mean, it's because the chart is really the FM response, the frequency deviation. At the when we say that the chart is C is equal minus alpha, we assume you only have a transient chart, which is not. And then we come in. There is also a adiabatic chart. What is that? And what is the?
You mean the difference between transient chirp and adiabatic chirp?
Yes.
As far as I understand it, the adiabatic chirp is the chirp that, because the chirp parameter is that one is derived from, like, you need a pulse in order to see that transient chirp and derive the chirp parameter. And that's transient chirp. But then the adiabatic chirp is the chirp that happens during, like, when you in the signal here in the picture on the screen, the adiabatic chirp would be the chirp between transients, as far as I understand it.
Yes, it's correct. And what physical mechanisms can cause this adiabatic chirp?
Well, during this period between, like, the signal is turned on, and that causes this rapid rise time overshoot ringing. And during the adiabatic chirp, you still have, or this period where you might see adiabatic chirp, you still have the ringing from the relaxation oscillations during that time period. So I guess it's related to that.
Yeah, maybe a little bit, but not mainly. Mainly it's due to very slow effects. I mean, more slower effects. So what slow effect can affect the wavelength of the laser? I mean, apart from that the carrier density is suddenly flat-based. But what can give it?
I'm thinking about spontaneous emission, maybe. Slow effects. Let's see. No, I actually can't think of it. My brain is empty.
Yeah. There can also be large fast effects giving adiabatic chirp. You can say adiabatic chirp is the chirp which is more or less proportional to the intensity, whereas the transient chirp is proportional to the derivative of intensity. So it's the slower effects and mainly spatial hole burning, and also gain compression.
Oh, yes.
Yes.
Yes. Okay.
Yeah. But
gain compression.
Then I wonder if you would compare a multi-mode fiber and a single mode fiber at 1060 nanometer.
Yeah.
And you would write how the reach depend on the bit rate. How would the curve look like? So we reach as a function of bit rate.
The reach is a function of bit rates.
Yes, so you have bit rate on the x-axis.
And reach here.
Yes.
So I can make it larger too.
Yes, yeah. And then we use sort of logarithmic axis. I mean, we bit rate there and reach on the y-axis.
Bit rate, reach, you wanted a multi-mode fiber and a single mode fiber?
Yes.
And let's see, speed, reach, let's see. Well, SMF, here we have 0. So, and this is back to back. I need to just figure out what I have here. So back to back, if I have with my 1060 nanometer systems.
Yes, with your 1060. So back to back, you can write on the x-axis, I think.
So I guess we only tried 2 kilometers.
Yes. Yes. No, there is bit rate. Sorry.
Oh,
so,
bit rate. Sorry.
Yeah.
That's see, I'm not used to this.
Yes.
So there, 2 kilometers, 1 kilometer.
Yes.
And let's see, we did.
And 1 gigabit per second and 10 gigabit per second, maybe, or something like that on the x-axis.
Yeah. Yeah. 10 and.
Or
did you say 1 and 10?
1. Yeah.
You want the logarithmic one?
Yes. Yes.
Yes.
So maybe 1 and 10 on the y-axis also. Or yeah, on the y-axis also for logarithmics. So 1 and 10.
That makes more sense because at 10 we can reach further than so I'm guessing with an SM we did get far away here. I see one. We have done this, so we've been up here and in this region and
So I'm more interested how fast, what before that point, and how fast does it fall? I mean, for a multi-mode fiber and a single-mode fiber. I mean, the single-mode fiber, which one is going the farthest distance, first of all?
The single-mode fiber should go the furthest distance.
Yes. And how fast does it fall after you reach that distance?
Well,
I mean, how if you increase the bit rate?
Well, I've never done it in this scale before, so it's very unintuitive for me. But let's see. So I guess it would be. This is so difficult.
I'm sorry. But before you come to the dispersion limit, at some bit rate you come to the dispersion limit.
Yeah.
What happens with the curve then? Is it completely flat, or I mean, is the reach constant, or does it decrease, or?
So before.
No, we can say at 1 kilometer, for instance, up to 1 kilometer for single-mode fiber. What happens then? Then you have no problems with dispersion.
Yeah.
Yes. So when you increase the bit rate up to 1 gigabit per second, does anything happen then with the reach?
Oh, okay. So at these very okay. So what we do have is I need to just have this as a in my inner eye, because at very, 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 very low speeds, it looks very much like this, and it doesn't matter much for the like a very, very low speeds that even at like 2 kilometers, if we're here somewhere, it will be fairly, let's see, if we're at the same reach, it would be fairly constant.
Yes.
Yes. So I'm just gonna do something like this.
Yes, it will decrease a little bit because you need the same, the noise increases because the bandwidth of your system increases a little bit. So it will slope a little, but hardly noticeable.
I guess
so,
if you
so at higher speeds, it's a little bit more difficult since you're need higher bandwidth of your receiver, so you get more noise.
Yeah.
Then for the single-mode fiber, what happens when you reach the dispersion limit?
So
and it drops, and how fast does it drop?
When I reach the dispersion limit, it starts to drop quite rapidly, I think. from experimental experience. I reach, because I can see a consistency in my measurements from 30 to 40, and then maybe 45, and then like it's, if I'm at 1 kilometer, then it just starts rushing down.
Yes.
So I guess reach at those, I mean, it would start to, this number is quite annoying, but I guess here somewhere it would start to like fall down.
And how fast is it? 10 dB per decade or 20 dB per decade?
Ah, okay.
Do you think?
Oh yeah.
For single mode fiber.
For single mode fiber. Okay. Oh, those units are, I haven't used those in a while.
Yeah, but that doesn't scale in proportional or inversely proportional to the bit rate, or does it scale proportional to the bit rate square, inversely proportional to bit rate square?
Okay, let's see. I would say the square.
Yes, and why is that?
Oh. Well, this feels like I should know actually. Let's see. There's this 4-bit chromatic dispersion, bit rate. I'm not. No, I can't dig that information out.
I know. Okay, it doesn't matter. But you know, when you have high speed, you get smaller distance between the bits. Of course, at high speed you have less tolerance to broadening, but also the broadening increases because the spectrum increases. So the problems with dispersion becomes worse. So you both get, I mean, higher, smaller distance for smaller tolerance for broadening, but also larger broadening. So that's why it goes like square.
Okay.
But for a single multimode fiber, you don't have that. Instead, you go not so far, but then it falls just bound over the bit rate. So it falls less steeply, but but you can't go as far.
I'm not sure where to put this in height.
No, you can put it at the same level,
At the same level.
But, yes, and then it will fall slower after you reach the dispersion limit. But yes, not so. It goes well. It starts to fall earlier.
Yeah, that's what I'm thinking. But I'm thinking, I mean, you can't come these distances. So you're thinking it would go.
Yes, something like that. But even earlier, I would guess.
Yeah, I don't really like the numbers. I would
Thank
like
you very
to
much.
do
I'm
this.
sorry about this, but thank you very much.
Because the numbers keep.
Let's go on to RIN instead.
Okay.
Yes, and then I want to focus on equation B12. I'm talking about this equation here.
Yes.
Yes. First of all, here, where does the amplifier noise come in? Is that included in the RIN, or is it in the thermal noise? Doesn't seem to be included in thermal noise. So
it's included in the total noise power. So he's talking about that first sigma total is a noise power that includes the entire system. But actually, you asked about the detector of the amplifier.
yes.
So actually, in this equation, you don't want the signal power. I think this one is you don't want to have the signal power of the amplifier included in your because you want to know the RIN of the VCSEL. So when I measure this, I measure a total signal power that includes the thermal noise. That's why we have to remove the thermal noise. It includes the shot noise as well. It includes the RIN, and so that's what we want to have. But when I measure, I also have the amplifier noise, and I have to, I guess it's included in this sigma total, because I have to, before I measure the RIN, I characterize my amplifier and detector.
Yes. So I think you include it in thermal noise, don't you? I mean, you subtract it from your measurement.
No, the thermal noise, well, it's like this. So, so the sigma total is the entire setup, everything. So the VCSEL is turned on, it's biased. So you have the VCSEL RIN, and you have the amp, and you have the everything included here. Yes. And then the sigma thermal is the everything again. Oh, it's included in both. And then
exactly. So in sigma thermal, I think 314 here, you should include the noise figure of your system, shouldn't it? I mean, because you really subtract the noise. You don't calculate the thermal noise when you do. You subtract you measure the thermal noise, and that includes the amplifier noise, I would guess.
That is true. Let's see.
Yes.
Yes. And so I subtract, so I measure the S21 of the amp and everything, and then I subtract it from the total, from all of it. And yes, it should include the noise figure, but I don't think we stated it in the equation. I'm not sure if that's...
No, it's missing in the equation 314. I think you should have a noise figure there.
Yeah.
However, there are other problems with 312, which are more serious, I think. If you do a dimensional analysis of it, so if please just do a dimensional analysis of all terms there, if you can do it.
Oh, okay. And so we have the noise powers here, and then...
Yes. What is the noise powers? What is the dimension of them if you look in 313, for instance? What is the dimension?
Well, the dimension.
Yes. I mean, Q is Coulomb. R times P0 is current, isn't it? And delta F is charge.
The responsivity is amperes per watt, right? P is watts. I think it's amperes per watt. And hertz, which is per second.
Yes.
And ampere seconds, watts, coulombs. Let's see, those disappear. I don't remember the code. Watt second, ampere, or is it ampere second?
Ampere is coulomb per second, so you can. I think the unit should be ampere squared, isn't it? It's the current variance you are different there.
Yeah, ampere squared. That's true.
Yeah. Yes.
Yes.
So all these sigmas, also sigma short, and sigma put and sigma pH, they have the same unit. It's ampere squared.
Yeah. What did we say? We said ampere per watts for the responsivity. And then watt squared, that's ampere squared. And then we have an omega here, which is, well, is volt per ampere or omega. I'm not sure if omega is SI units. Ampere. So I guess we get amperes per watts.
Yes, and it seems strange, isn't it?
Did I miss something?
Yeah, I can say the problems here. There are several problems. First of all, you have defined sigma shot in another way than you did in the paper. So sigma shot here, as you define it here, should be above the fraction bar. It should not be on the side of the fraction bar.
Oh, it's because it's defined differently, yes.
Yes, and the RL in the denominator should not be there. There should be delta F instead, because this should be it should be per watt, per
we have an errata.
It should be the unit V of RIN. So there are several mistakes in this formula that you maybe want to.
So maybe one mistake made me do several mistakes.
Yeah.
That's not good.
Well, I think they are independent.
Yeah.
You have even in the paper, I think, but and that is that you say that it's hours, and then it's you know, you want RIN to be per hertz.
Yes, that's true.
But in the paper it's correct with this shock noise as you have written it, because there you have defined the shock noise in another way.
Yes.
Yeah.
That's why I was confused. Okay.
Yeah.
So
yeah,
I
it's always good to make a sort of dimensional analysis when you have a formula. Because I understand you have measured this, and what you have measured is correct. It's just when you put up the formula.
Yes, I appreciate that you found this.
yeah, you're very welcome. So yes, otherwise I have no questions more than what your plans are after this. Will you stay at Chalmers or?
I'm hoping to be able to continue work with VCSELs or transceivers for high speed, maybe disaggregated links, but I'm hoping to do that in the US, where there's plenty of companies pushing the state of the art. So I'm looking for a job.
Oh, I see. Yeah. So maybe you go to 80 labs or something like that. So thank you very much, Eva. So that's all my questions. Yeah.
Thank you.
Thank you, Richard.
That was tricky, but it was fun.
Yeah, that's good. A bit of excitement here. Do we have Lena Wosinska online from Chalmers?
Yes, I'm here.
Okay, great.
Yeah, so first of all, thank you, Eva, for a nice presentation, and I'm delighted to be part of the grading committee for your thesis. My research, one of my research areas is also optical interconnect in data centers. So in this sense, kind of similar as yours, but my focus is more on architecture design and optimization, and also resource allocation. So I don't focus that much on component technology like you do. So my questions will be more related to some, we will be not that much, let's say, theoretical as Rickard's, so you can relax now. Okay, so in figure 1.2, and also on your 5th slide, you showed some architectures of also topologies and architectures.
Yes, in the introduction. I hope you all on YouTube, but that you actually went ahead and downloaded my thesis, because I sent the link to it. Yes, page 1 and 2. Oh, 3. Figure 1, 2.
Slide 5 in your presentation, but maybe you can
go to I can go to the presentation, of course. Sorry.
There are, in fact, two different, slightly different architectures, but
did you mean the spine leaf?
No, but maybe you don't need to show. Just I would like to ask you if it was any reason that you selected this to show, or
the spine leaf, or the factory.
Yeah, if it is a certain reason that you show, because there are plenty of architectures that are proposed in different places, including our group. But
this is actually something I would like to ask you, because I was reading a bunch about the factory topologies, and they have a long history in data center networks. And with history, I don't necessarily mean time, but I mean there are many iterations of the factory topology. And they use advanced mathematical structures in order to come up with these topologies. And this spine leaf topology is fairly a new iteration of the factory, where they have a very heavy there are lots and lots of connections between these servers that are the spine servers and the leaf servers, and then you have the or switches, I mean, not servers. And then the servers are connected in clusters and also are heavily connected in between each other. And the reason why I chose to show this one is partly because this topology allows for switches that are, they don't need to be very complex or large or have very high switch capacity. You can, since you can have many more of them and have many connections, they will not have, as I understand it, as high as a load at the same time. So you can have reduced requirements on these switches, but have more of them. And this, the reason then, partly that, because that reduces, could reduce cost if you don't have to have these really advanced switches. And then also this topology requires a huge amount of connections, optical interconnections in between these levels, and a limiting factor there is the reach of a single optical interconnect. Like if you don't have long enough optical interconnects, this architecture won't scale at a certain point. But I wanted to ask you if this is actually a relevant topology to show, because I tried to look into it, but it's a big research area in itself.
Well, the advantages and disadvantages of all proposals for architectures, of course. For this topology that you mentioned, I think the main advantage is that there is a high survivability or reliability of connections, because then if something goes down, then you can use another path, and there is a variety of choices. But my question is also, you consider that the switches are optical also. So you consider the transparent connections between servers, or between top of the racks, or between pods?
Right now, Yeah, right now I'm considering them to be electrical because that's what I believe is available. I do think optical in this type of topology and optical switching would be immensely beneficial. So that would be, yes, that's a potential of this architecture.
Assume transparent interconnects between servers and or tops of the rack.
All right.
They try to eliminate this aggregation tier in the data center. So from top of the rack you go to the core switch directly.
Mm-hmm.
So this is the main trend, and also it saves a lot of energy because in addition, if you have electronic switches in the aggregation tier, it will take a lot of energy, and you would need to have a lot of interfaces and so on.
Okay.
So this was my first question, and the second one is so your since you assume electronic switches, so you assume the switches on packet base by packet basis, right? Mm-hmm. So this is what the optical switches will not do. Basically. Yeah. My other question is if you have some thought about free space interconnects, optical free space interconnects, in particular in data centers. I think it is kind of interesting approach, but how your VCSELs would then fit to this? Do you think it would be interesting for interesting application for VCSELs?
Wow, I'm not really sure how the free space interconnects would function. I guess, is that for very short distances or?
It can be. I mean, that doesn't need to be very short, but maybe not in on the order of tens of kilometers. But I think hundreds of meters, 1 kilometer should go.
All right. Well, the 1060 VCSELs that I have fabricated have beam divergence that would not allow for that communication. I guess with the correcting optics, you can do a lot, but I'm not sure what the ideal light source would be. You would certainly want something that's highly directive. Yeah, I've never actually considered free space. Is that something that's that is an oncoming trend, or is it something that has been used before?
Does it save on cabling? I mean, as you shown, or no, in fact, I think the opponent shown in his slides.
Yes, in the introduction.
And it can be a solution to minimize or to limit the cabling. And I have seen some presentations, I mean, on the conferences where they suggest to apply free space optics.
I guess, I mean, in these data centers, we need a lot of different technologies in order that compensate each other. You can't go with one technology for all distances, all purposes, all lengths. So you need to have probably a combination between, and the free space optics seems to be one of them. I guess they use a different light source, but I wouldn't be able to give my I'm not sure how these systems what the transmitter looks like, so I don't dare to say what kind of light source should be used.
I was asking because at this conference that I mentioned, they referred to advantage that they experimental, they use some different lasers, but they complained that they don't have access to VCSELs. They would be better.
Yeah, I can imagine that these transceivers can be made quite bulky, and that by now, like today, maybe like you can do it with a bunch of. What I want to say is that I think they can be made with a various, like many different kinds of light sources. You can add optics and add things in order to make it work. But what is the most ideal light source? As I said, I think it would be something that can be highly directional without as many correcting. It should probably also have the energy efficiency in mind. And VCSELs are energy efficient, so I guess it's a good option. Yeah, so and if they are complaining that they want VCSELs, then probably VCSELs are good. But actually, I'm gonna pick up an article on that and see how those transceivers are built or transmitters are built. Yes.
Yeah. So another, I mean, it's more like a comment, because you mentioned that you also applied forward error corrections and DSP, but regarding latencies, I mean, in the data centers interconnects, latency is very key problem.
Yes.
So I think it would not allow for this kind of.
In my publications, we haven't used forward error correction in any of the results I have published. We have used equalization, and we have used pulse shaping. And pulse shaping is, as you say, something that might not be, it's not optimum in a data center. I'm not sure if, I did write a little bit about it in the thesis, but I don't remember if it adds latency, but I do know it adds to power consumption and bulkiness of the transceivers. And equalization can be made fairly simple with few taps. You don't have to have it both in the transceiver and transmitter and receiver. You can try to minimize equalization. But yes, I do think that we should aim to have as little tricks, so to speak, going on, and make the circuits as simple as possible. Just due to the power consumption, latency, congestion, like the actual space that the transceivers require. So that's why I try to make my transmission measurements in such a way without using equalization or DSP of any kind, or analog either, signal processing.
Also, I mean, you refer to, I mean, as a motivation for your work, you refer to increasing capacity, I mean, requirement for the capacity in the big data centers.
Yes.
But in my understanding, it will be, in the future, it will be a bit relaxed because of the latency issue. So instead of have a few big data centers, it may be better to have a number of small data centers. So
yes, that's why I think actually the switch that I recommended to you to take a look at, I don't know if they're a brilliant company, but I do think their marketing is brilliant. And they are focusing, they have 4 sites in the US, and their biggest one is actually, as you say, several, it's not the biggest data centers in the world, but they are still hyperscale data centers. But they connect them, they have, each data center might then have better latency requirements, and then they can connect them and make a bigger network out of several fairly huge data centers.
And also to have smaller data centers close to the users. This is, I mean, to reduce latency of
oh, you mean between the user and data center? Okay.
Yeah, of course, there is a trade-off for energy efficiency, because if you have big data centers, it's more energy efficient than to have a lot of small data centers. But
okay. Yes. I'm not sure how. I think that's a future development that we will see. But I don't think. I think we will still have a few decades, 1 or 2, with the developing these large data centers for sustainability, because if you just do the helicopter perspective, usually when you have a new technology or a new industry, first everyone has not first, but in the beginning, everyone has like small, like businesses have their own. In the data center, we've been having lots of small data centers, like server rooms, at many companies over the world. And as they develop, they start to conform. And usually businesses do conform after a while. And then after they have conformed, and a new technological breakthrough can make the technology more like ooze into our daily life, like in a more integrated way. So the technology in the future will become more integrated with our lives. And as you say, maybe the first step towards that is smaller data centers closer to the end user.
It's already happening. I mean, there are almost, I mean, now for the 5G, let's say, technologies, they are talking about data center in all base stations, let's say so.
Yes, but what if in 50 years everyone had a small base station in between their walls? So maybe that will happen. So that's what I mean. That's happening already, but I mean that it will become even more integrated, so that we don't even see it. That's. I'm sorry for being a bit up there in the air, but that's how I would like to see it.
Yeah. So my final question is then more from my curiosity. In figure 4.2, you present refractive index and optical intensity in the longitudinal direction close to the active region.
Yes.
So basically, the oxide apertures are formed by oxidation, where aluminium-rich layers oxidize faster, right?
Yes.
But here I'm not very clear because this aluminium would also change the refractive index, in my understanding.
Yes.
But the refractive index here is kind of the same, while the oxide aperture have different length. So
yes, it's a 2% difference in aluminium content. So the refractive index is pretty much the same, but the 4 secondary oxide apertures have 96% aluminium, and the 2 primary have 98% aluminium content. So the difference in refractive index is very small compared to the oxidation rate. Yes.
But simply, it is not this. the figure didn't show this small difference. So it's like.
Well, 98 and 96% can be. This is not the. These are on the screen. I'm not sharing it with you, but here we see for secondary oxides, and the primary actually are oxidized somewhere far into the left. And this is what happens along the edge because these layers have 90% aluminium in them. You can see a slight tiny difference in refractive index. It's probably like 0.5 millimeter or less, but I can see a slight difference. But it's a good question because it's interesting how sensitive the oxidation rate is to the aluminium content.
Okay, so this was my final question. Thank you very much.
Thank you very much,
you,
Lena. So, does anyone else in the committee have any questions that you forgot to ask? Our proponent might have something still. So is the committee and the grading, is the grading committee and the opponent happy so far with the answers? Then we will go to the audience here to see if we have any questions from the few people in the room. Do we have any questions here?
Can I ask?
Yeah.
Sorry but I fatigue you with my question.
No, that's fine.
Anyway, I'm not very familiar on your topic, but my investigation is connected with multiple fibers, transmission.
Yes.
Fiber.
Oh.
So I'm very interested. Is it some future with VCSEL, which is connected to multiple fiber?
Yes.
Okay.
So it's a very good question. So what I use is a VCSEL with a single core. So you can do many things to aggregate the capacity from this. So as I said before, you can add several links next to each other like this. So standard is to have four fibers next to each other, and then also in each center you can add multiple wavelengths, lambda 1, lambda 2, and you can do that here as well. Up to today I spoke about 8 wavelengths, for instance, as an example. And another way of doing this parallel lines, so this takes up space, right? And transceivers will be bigger. So what you can do instead is to do what you are researching, is to have a different kind of fiber that has, I don't know how many cores you're using, but you should be maybe using 6.
I investigate 3-core fiber.
Ooh, 3-core
right
fiber.
now.
That sounds cool, but I've seen some that have 6. I haven't seen 3, but that's probably a reason behind that. But then you can transmit, instead of having 6, or in your case 3 fibers next to each other, you can transmit them in one core. And also the difference then, here we have a regular VCSEL, like a separate VCSEL structure. From the top, looks like I usually have a contact, and then you can probe it. Sometimes you make the pads square, and you add signal and ground to it. But these can be made in VCSEL arrays, where you have an area where you probe, and then you can position the VCSELs next to each other and control them on the same chip, so they take much less space. I mean, this distance here would then be matching that there. So you can drive all of the VCSELs using the same paths, at least I think. I'm not sure. Anyways, they take up less space. So it's a benefit. You don't need to have parallel, and then you can also still use several wavelengths in each core and have a high capacity, a very high capacity.
Okay, thank you.
So we have an online question here by Stavros Giannakopoulos. Is that from the group?
He's from microwave electronics group.
Yeah, okay.
Not from photonics.
So the question is, are there other areas, applications of these VCSELs besides fiber optical communication?
Well, you can use them for sensing applications. I measured very low line widths on my VCSELs, and the low line, a reduced line width is good for applications where you need a very small spectral width. So in sensing, you can also use VCSELs in applications where you have atomic clocks. There are several applications, but those are the two I can come up with at the moment.
And then there's a question by Åsa Haglund.
Cool.
There are two tweets here. The detuning on the VCSELs affects most of its performance, such as modulation speed and energy efficiency, that are important in your work. I didn't find any information about the tuning of the VCSELs in your papers.
No.
What is the detuning in your devices? Is there any room for improvement by optimization this further?
Yeah, there's room for improvement. The detuning that Åsa speaks of is measure between the photoluminescence peak of the active region. So the wavelength of which the active region will have a luminescence peak, and the DBRs have a different frequent wavelength where they have a resonance. So the difference between let's see, I think. So this is the gain of the VCSEL, and this gain peak is related to and a little bit estimated by a photoluminescence peak. So this is wavelength here. So at a certain wavelength, you will have a peak in the gain of the VCSEL, and then the photoluminescence peak. They can't measure the gain peak when they fabricate the material, so they measure something called the photoluminescence peak instead, which is a peak that when they use a spectrometer, they grow the active region on a substrate, and they look at where, and they inject carriers, I think, and look at what wavelength. They scan the wavelength to see where they have a peak. So this peak is 1045 roughly, or was designed to be 1045 in our devices, and it should correspond roughly to the gain peak. And then we have the mirrors, which, well, that's a bit exaggerated, but the entire structure with the mirrors will experience a dip, a resonance dip. So the structure will have, the DBRs will make sure that you have reflection that has such a certain bandwidth, And in this spectrum, this is also wavelength, you will have a resonance dip, and that dip is 1060 nanometers, roughly for us. So the difference between these, because when you add the mirrors to the gain, and you will get a lasing wavelength, so the resonance wavelength might be here, and the main peak is here. So the difference between these will be the detuning, which is 50 nanometers in my case. And when you start to bias the VCSEL, these peaks will move, and they move at different rates with temperature. So when you bias the VCSEL, you will have a point where your current threshold is at the minimum. And when I measured also my VCSELs, I found that the minimum threshold current was closer to 0 degrees, which indicates that the detuning was not as expected, I think. It should be, it shouldn't be that low. So there's room for optimization there, absolutely. That's why partly what I think is so exciting with my research is that this is the first iteration of 1060 nanometer VCSELs we've done at Chalmers, and they are the best in the world. So, and this is not an optimized, I mean, it is based on a truly great 850 nanometer design, but it's not, it hasn't been optimized further. So there's room for improvement, and I think that's really exciting.
Okay, thank you very much, Eva. And thank you also, and Stavros, for your questions. Do we have any more questions coming up here?
I have a comment, if I may say.
Yeah, I probably
this that you say that the gain peak and the photoluminescence peak is about the same wavelength. That is not true, really.
It's related, kind of, I think.
Yeah, it's related, but the photoluminescence peak is on higher energies, so that's shorter wavelengths than the gain peak, and that's quite important. Yes.
So yeah, and that makes sense because it moves 3 times faster roughly than this. So if it was 1045, the detuning would be all weird. So there it is. So yes, so good comment. So this is actually, yeah, this peak is still here, but it's then lower than the PL peak.
Exactly.
Thank you, Rika. I know they're related, but you should have asked me how, and I wouldn't have been able to answer.
Okay. I see no further questions on the chat line here, so if there are no more questions, I think we would like to thank everyone who has participated here, especially our faculty opponent and our grading committee who did great work here. And also for you out there in the cyberspace, staying with us this far. So thank you very much. Now what will happen is that we will have the grading committee and the opponent and also the supervisor to have a separate meeting. And with that, thank you, Eva.
Thank you, Dag.
And thank you also, Henrik, for
I've made a slide.
Arranging all these things. So with that, let me close this session. Thank you very much.
Thank you.
So maybe the chair could tell the decision here. So I think now we're back. We are all back here now. So we're eager to listen to the verdict.
You want the YouTube channel up for this?
The YouTube channel is up for this. Now it's streamed across the whole world. So I hope you stay with the decision you just told me.
I hope she won't cry.
Yeah. no.
So Lena, maybe you as
Okay.
as the chair should convey the message.
Okay, I was selected to be chair of the committee, so it's my pleasure to pass the result to you, Eva. So anonymously, you were you have passed the exam.
Yay!
So congratulations.
Thank you so much. I can feel myself.
So with that, we'd like to thank you all for helping out with this dissertation, and I think there's nothing else to it more than weekend coming up, so I wish you a good weekend here, and thanks for all your help. And
Yes.
we will see the decision coming both digitally and in paper format eventually. So thank you very much.
Cheers, Eva. Cheers.
Thank you so much. And I really, you've been an awesome committee and opponent. I enjoyed your questions. They were all very relevant. So thank you.
Yeah, thank you very much, Eva.
Congratulations.
Thank you.
Thank you. Bye-bye.
Bye now.
Congratulations, and relax now, Eva.
Yay.
Okay, so let's do this one.
Exactly.
Congratulations.
Grattis.
Thank you. Oh. Thank you.
Så vi,
Okay.